Okay, so in this problem, we want to show that if b is greater than 0 and a equals b times q plus r, we want to show that if these statements are true, that the GCD of a, b is equal to the GCD of b, r. So here we're going to deal with divisibility and greatest common divisors. And just note that this notation, these parentheses with the a and the b, in my textbook, when they write it like this, it means the greatest common divisor of a and b. You might also see it like this. It just depends on what book you use, but just know that don't confuse this as a coordinate. This is the GCD of A and B, meaning the greatest common divisor that divides A and B. So here we're going to use a proof technique. We know we're dealing with divisibility because we have, this statement here that shows that A has this linear relationship with B, Q, and R, B and R with Q being a multiple integer. And we know that we're trying to show equality. So real quick before I even start the actual proof, I just want to note that already in my head, I know the road I'm going to be going down for this proof because I know that if I want to show equality with divisibility, and we're going to be using divisibility here because we're using divisors, I know that if I want to show the greatest common divisor of A and B is equal to the greatest common divisor of B and R, then I can show that the GCD of AB divides BR and the GCD of BR divides the GCD of AB. If I can show that these two things are true, then I know that they're equal. Think about it like this. Just say two integers A and B. If A divides B and B divides A, this implies that A equals B. Because when you see A divides B, like 2 divides 4, 3 divides 6, those, you're basically saying that A is less than or equal to B. So if we say A is less than or equal to B and B is less than or equal to A, the only possible outcome is that A equals B. So this is what we're going to want to show, these two things. So just keep that in your mind while we're going through the proof, and whenever you're trying to look at a proof and say, well, where do I go with this? Just think about, okay, well, my ultimate goal is to prove equality. Well, how am I going to prove that? Well, with divisibility, this technique is like should be the first thing that pops in your head. Okay, so let's actually start with a proof and the formal proof. And remember, when we start with a proof, we're gonna write down what we know. So we know b is greater than 0, and we know a equals bq plus r. So let's write that down. So let's let b be greater than 0 and a equal bq plus r. So we want to get on the path where we're showing that this is true. So let's rename, let's say the GCD of AB is equal to D1. That's just an arbitrary choice I chose. So suppose D1 equals the GCD of AB. That's just going to be a little bit easier to deal with. One variable instead of writing all this. So D1 is AB and D2 is the GCD of BR. Okay, so we know by definition of the greatest common divisors that if D1 is the GCD of AB, we know that D1 divides A and D1 also divides B. Same with D2. D2 will divide B. It also will divide R. That's just by definition of greatest common divisors. So that's something also you're going to need to know. You need to know these facts to be able to continue, chugging through the proof. So here we're going to say, since D2 divides B, and D2 divides R, then D2 divides BQ, meaning if D2 divides B, then it will divide any multiple of B, where Q is just some integer, 1, 2, 3, 4. Then D2 divides BQ, and remember our A is BQ plus R. So we said, well, it divides B and R. It also divides BQ, because if D2 divides B, then it divides a multiple of B. Thus, D2 divides BQ plus R. Well, since BQ plus R we know is equal to A, then we know then D2 divides A. Okay, if this is becoming a little confusing for you because we're just throwing around, different variable names, and you're not super comfortable with dealing with divisibility yet, put in numbers. So if we said, okay, B and R and D2, let's say 3 is equal to 3, the GCD of 3 and 6, which is true. Well, if you needed kind of convincing that the GCD divides both numbers here, 3 divides 3 is true, it's 1. 3 divides 6 is true, is 2. So we know 3 divides 3 and 3 divides 6. So also, if you need convincing that 3 divides any multiple of 3, so let's say 3 divides 3 times m, where m is any integer 1, positive integer 1, 2. So think about this. 3 times 2 is 6. 3 divides 6. 3 times 3 is 9. 3 divides 9. 3 times 4 is 12. 3 divides 12. So that's true. And then if we want to see that it divides a linear combination, 3 divides 3 times m plus 6. M is 1. This equals 9. 3 divides 9. M is 2. This equals 12. 3 divides 12. So if you ever are like, you're kind of trying to trudge through it and you can't quite see it, plug in some numbers and try to visualize it. So this is just kind of an aside. This isn't really part of the proof. Okay, so we know D2 divides A. We really wanted to show that D2 divided by A because D1 has A in it, and that's how we're going to relate D2 to D1. So you need to be saying in your head, well, how can I relate D2 with D1 to finally show that D2 divides D1? Because remember, that's the first step in showing equality. So here we've related D2 with A. So since D1 is equal to the GCD of A and B, and we showed earlier, just now, that D2 equals A, well, then we know that D2 divides D1 because D1 is the GCD of A and B. D2 divides A. So we know that D2 must divide D1. And like I said, plug in some numbers if you need convincing of these things. So D2 divides D1. That was the first thing we wanted to convince ourselves of. Remember up here we said, okay, well, if we can show A divides B and B divides A, then A equals B. So we've done the first step here. We've showed that D2 divides D1. So now let's do the exact same method going the other way. So we can show that D1 divides D2, and then we can show that they're equal. So remember here we said, okay, since D2 divides B and it divides BQ and R, then D2 divides BQ plus R, then D2 divides A. So let's use that same strategy, but it's just going to be a little different because we're going to use D1. So here's how we're going to do this. So since D1 divides B, because D1 is the GCD of A and B, then D1 divides B times Q, since this is just a multiple of B. And since D1 divides A, because D1 is the GCD of A and B. And let's make a side note here. A equals BQ plus R. Here we know that D1 divides A and BQ. So we want to get it in terms of R. So R equals, just subtracting the BQ over, we have BQ minus A. Okay? So that's just a little side note. So we know that D1 divides BQ. Also, it divides A. So then D1 divides A minus BQ. What do we say? Whoops, this should be A minus BQ. Okay, so D divides A minus BQ. Then A divides BQ. Thus, D1 divides R. Well, that's convenient because D2 is the GCD of B and R. And we know D1 divides R. So, since D2 is the GCD of B and R, and D1 divides R, then D1 divides D2. Well, okay, so now here we have D2 divides D1 and D1 divides D2. Now remember, if we're saying D2 is less than or equal to D1 and D1 is less than or equal to D2, well, they can't both be less than the other, so the only option is for them to be equal. So D1 and D2 are both positive integers. GCDs are positive integers such that D1 divides D2 and D2 divides D1. Then D1 equals D2. And remember, D1 and D2 were just stood for the GCD of AB and the GCD of BR. So, therefore, the GCD of AB is equal to the GCD of BR. And that was what we wanted to show. So that concludes our proof. So it just takes a little bit of practice being able to recognize what needs to be done. When you see the original problem, you wouldn't necessarily think that that was the road you needed to take. But just remember, when you're working with congruences, with divisibility, and you're working with GCDs and you're trying to show equality, almost always you're going to want to prove that one divides the other and vice versa to show equality. Okay? And then just list your knowns. And, with proofs, you're going to sometimes have rough drafts. You might go down one road and it doesn't take you anywhere and you need to go down another road. Just trial and error. So, just stick with it and you'll usually figure it out, 3 pages later.